Hi guys, this is Hans from TechMe Academy. Today we're going to take a look at series parallel mesh circuits, as well as calculating the current flow in each one of the branches, total current flow seen by the source, as well as total power consumed by the circuit, and circuit analysis with the basics of Kirchhoff's current law. I hope you guys enjoy.
So I have this, and we have a battery over here. The longer side is obviously designated as positive via IC, so we have conventional current flow within each and every one of these branches. But we just got to look at the total. So the total will obviously be flowing here, and the total will be flowing here. Some of it will be going down here, some of it will be going down here, some of it will be going down here. This is current flow. So the concept of current flow will be demonstrated in this parallel circuit. So now let's look at how much current will flow in each one of these branches in the mesh. So currently we have three branches. We have 10, 5, and 10. The simple thing about this is we have no inline series resistances. So that makes it quite simple. We know that the total voltage will drop over each and every one of these because of their parallel nature, right? Deliver a certain voltage across that resistance, which is in this case 10 volts. And the same with the 5 and the same with the 10. So now let's look at it quickly. So let's go and state that our current in each one of the branches is going to be I equals V over R, which is Ohm's law, right? 10 divided by 10 is this one over here. 10 divided by 5 is that one over there, and 10 divided by this one, 10, is this I3. So equals I1 equals I2 equals I3, right? The branch current. So our first current was 1, 2, and then 1 amp. All right, easy. So the next thing we got to do is look at IT. Now, if we look at Kirchhoff's current law, which basically states that all currents that flow to a node will be equal to the currents flowing away from a node. What this algebraically means is that these will all be additive for IT because of the parallel branches adding, flowing back to the battery. So it'll be 1 plus 2 plus 1 equals 4 amps. Will be the total current flowing out of the battery. That's how much the battery has to provide this circuit. So if your battery is not rated at 4 amps, in this case, it will not even provide this. But we are working in a perfect environment here, and we're also pretending that the battery has no internal resistance. So for all T's and C's, 4 amps. Okay, so the next thing is we got to look at the total resistance seen by the battery, or seen by the circuit from the front two terminals, which will be 1 over plus 1 over plus 1 over what? Right? 1 over 10 plus 1 over 5 plus 1 over 10. And let me be quite frank, right? The biggest thing people get wrong about the parallel formula is remembering that it's 1 over RT. It isn't just RT is equal to 1 over all of the other stuff on the right-hand side. So what you're left with is a flipping scenario. If you flip 10 over 4 and you flip RT over 1, anything over itself is just itself. So RT will then essentially be equal to 10 over 4, which is equal to 2,5 ohms, right? All right, so let's go look at the power formula quickly. So P is equal to IV, right? This is the simplest one that I taught you guys, which is essentially, let's go and look at the total current flow for times the voltage is 10, which is equal to 40 watts, right? Okay, cool. Now we've used P equals IV, but if we look at the wheel, we can write P as a few things. Let's express it in not in terms of current, but in terms of voltage and resistance. And let's see if it proves to be true. In the second formula for power, we're going to use V squared over R, which is mathematically all derived from Ohm's law and the power equation. So these are all on the wheel I showed in video 1.1. So we're going to go 10 squared over the total resistance of the circuit was 2,5, which is essentially 100 divided by 2,5, which is essentially 40. Right? Even this can solve it for us. So, which is essentially 40. You're done with parallel resistances, and we're just going to take a look at a parallel series combo and how to break that down as well. Let's go look at another equation. So say we have the exact same 10-volt circuit here, right? And I put a resistance in series, and we have our same three that we had, right? Which we already know what they are. 10, 5, that's 10. And we add a 10 ohm resistor here. Right. So essentially what will happen here is the voltage will drop over this 10 ohm, but only to a certain degree in proportion to this over here summarized as another series resistance. This entire piece of the circuit is essentially equal to, as seen by the source, at 2.5 ohms. Alright guys, just taking another look at a slight curveball in the equation. If I put in the series resistance with what we've already had, which is 3 in parallel, what will happen? Alright, what will happen to the circuit? Let's go through that. It'll change the resistance total seen by the battery. The resistance total is equal to 2.5 of this, which will not change. Now we've ohms. That is the equivalent series circuit of that, if we had to put it in the circuit. So obviously this whole mesh equates to 2.5 ohms. All right, so what does that do to the total current of the circuit? Essentially what the source will see is the series resistor, which we've claimed to be 10 ohms, in line, in series, with a 2.5 ohm resistor, right? This is what your circuit will essentially simplify to. This is why I said we're going to start with simplifying basic resistances. So your circuit now will see a 10 and a 2.5 ohm resistor. The total current draw will be, let's go back to Ohm's law, I equals V over R, which is 12.5, which essentially will be 0.8 amps. All right, so that concludes today's lecture of parallel resistances, parallel and series combo, and then also simplifying the circuits. I hope you guys enjoyed it, and I'll see you guys soon for another one of TechMia's videos. Thank you.